So I just wanted to do a hopefully quick example of a parametric curve that has trig functions in it. All right, and do some calculus problems with it. All right, so let's say I have these two equations right here for my x and y, and I'm told to do some algebraic calculus stuff with them. So let's find all the intercepts of the graph. Let's find the horizontal tangents. Let's find the vertical tangents. Now what I would do is I would graph it first, all right, to get an idea about what's going on. And so I've preset this up. So here's my equations right here that I'm trying to graph. Let me try to get the glare out of it. So here's my equations, and remember, you want to think about setting up the window. With trig functions, if you just have trig functions, you want to try to graph it from 0 to 2 pi initially. I did my t-step at pi over 50 just to try to get a smooth graph out of it. If you notice, my x's are between -2 and 2, and my y's are between -3 and 3, so I just set up my x's and y's that way. Now the nice thing is, you want to try from 0 to 2 pi, you might be able to notice some shortcuts, and I actually did on this one accidentally, and it made doing the math a lot simpler. So if I go and hit graph initially, I get this strange graph, but notice right here, my calculator's still graphing. All right, that means the graph's just repeating itself. So if you see that, now there's going to be two things. If you don't see what looks like a complete graph, I would make your t window bigger. But in this case, I saw that it was repeating itself, so I just tried t equal to pi to see if I would get the same graph. And look at this. And see, it stopped right then. So that means that graph is doing one complete cycle from t equals 0 to pi. So that allowed me to simplify things out a little bit. But if we draw the graph in here, you can see that it looks like this. Some things to notice, that it started here, wound around this way, like that. There's my orientation to indicate that. All right, now you can kind of get some build up to what all you're going to need. Finding all the intercepts. Notice that there's only 2 x-intercepts, but there's 1, 2, 3, 4 y-intercepts. Horizontal tangents, you have a horizontal tangent here and a horizontal tangent there, so we would expect 2 horizontal tangents. But if you look at the vertical tangents, there's 6 places where I'm going to get a vertical tangent. So that's what we can expect. Now I will caution you too while we're here. Some of these things you can see just from the graph, but practice going through the math. And I promise you, A, you will see more complicated ones. B, I can give you more complicated ones if we're shortcutting the process all the time. Okay, anyway, so there's what we can expect to happen. So let's go through and show how to make it happen. All right, so for x-intercepts, remember we're setting y equal to 0. So we take our equation for y. There's no calculus here. Take our equation for y and set it equal to 0. Divide by 3 to get sine 2t equals 0. So you ask where the sine is equal to 0. That's at 0 and pi. And then, so it's 0 and pi, but then we have to add on what I call the circular adjustment. That's just accounting for rotations. But our angle here is 2t, so 2t would have to equal these two expressions. So now you go and divide by 2 into our two expressions, and you divide the 2 into both parts, and so you end up with 0 plus k pi and pi over 2 plus k pi. All right, now what's key here is I noticed that shortcut. You could do this from 0 to 2 pi. You're just going to get a lot of repetition in your work. And so I noticed I could graph this between 0 and pi. That means I'm only looking for t values that are in that interval, 0 to pi. So if I do k equals 0, I'm going to get 0 and pi over 2. But if I do k equals 1, I'm going to get pi. I need that one. But if I do k equals 1 here, I'd end up with 3 pi over 2, which is outside of that range, so I don't need to include it. All right, now we need the xy coordinates for these, so we plug in t equals 0. If you trust your math, you know y is going to be 0. So this is one I didn't show my work, but I did later. So if I'm plugging in t equals 0 for x, I'm coming up here and plugging in t equals 0, so I have 2 cosine of 0. Cosine of 0 is 1. So you get x is equal to 2. If you plug in t equals pi over 2, you get negative 2, 0. And then if you plug in t equal pi, you get 2, 0 again. That's a repeat. If we're just asking for x-intercepts, there's only 2, which we expected. So there's our 2 x-intercepts. Now for the y-intercept, we set x equal to 0. So we take our equation for x and we set it equal to 0. divide out your 2. You ask yourself, when does the cosine equal 0? It's at pi over 2 and 3 pi over 2. And you add in your circular adjustments there. Now, to isolate t, we got to divide by 6. So we got to divide this by 6 and this by 6. And so you get pi over 12 plus k pi over 3. Whenever you divide this by 6, the 2 and the 6 reduce. All right. Same thing here. I got to divide this by 6. And so I get 3 pi over 12 plus k pi over 3. You can reduce this. Just in a minute, though, I'm going to have to substitute in k, so it's better to think about those with their common denominator forms. Okay, so we're looking for solutions in 0 to pi. And so what I did is I went to this first set. For k equals 0, I just get pi over 12. For k equal 1, I went to my common denominator form, so I have pi over 12 plus 4 pi over 12. That's 5 pi over 12. For k equals 2, I have 8 pi over 12 plus 1 pi over 12. I get 9 pi over 12. If I tried to plug in k equal to 3, I would end up outside of my range, 0 to 2 pi, or 0 to pi, sorry. And then I go to this set of solutions. It's easier to do calculations with this, but then you reduce in your answers. So k equals 0, I get pi over 4. K equals 1, I would have 3 plus 4 is 7 pi over 12. K equals 2, I would have 3 plus 8 is 11 pi over 12. So there's those 6 times that we're seeing y-intercepts. So now you just got to plug in each one of them. X should be 0 each time. So one way you can do is use that to check. The other way is just to hopefully assume your math is good, but you might want to at least check 1 or 2. So you're plugging in t equals pi over 12 into your x, y equations. So I'm plugging in t equals pi over 12 here. That 2 is going to reduce it down to pi over 6 though. And the sign of pi over 6 is 1/2, so we end up with 3 times a half, or 3 halves. So there's our first y-intercept. All right, now I just need to go through and plug in each one of these. If I plug in t equals 5 pi over 12 for my y, notice that I have that 2 inside of my sign, and so I'm going to get 10 pi over 12, which reduces to 5 pi over 6. Sign of pi over 6 is also a half, so we get 3 halves. So there's a repeat. Plug in 9 pi over 12, you end up with 3 sine 18 pi over 12. Now you end up with the sign of 3 pi over 2 there. That's -1. So there's another y-intercept of 0, -3. Plug in t equals pi over 4, that's this one. You end up with 3 sine pi over 2, which is 3. So we get 0, 3 there. Plug in t equals 7 pi over 12. You end up with 7 pi over 6 as your angle. The sign of 7 pi over 6 is -1/2. So 0, -3 halves. Plug in t equals 11 pi over 12. We actually get a repeat there. 0, -3 halves, which we just saw. All right, and then that's all of our lists. So what are the y-intercepts? There are these numbers, these points right here, which we expected. We expected 4 y-intercepts. All right, now we go to horizontal tangents. All right, so here's my equation for y. Oh, I wrote it over here. So, okay, so remember for horizontal tangents, we're setting dy dt equal to 0. Here's my equation for y, so I got to differentiate it. Sine differentiates to cosine. So, but we got to use the chain rule. So we have 3 cosine of 2t, but then we differentiate the inside. So we end up with 6 cosine of 2t equal to 0. You divide out the 6, you get this. And so now you're asking where the cosine equals 0. That's pi over 2 and 3 pi over 2. But our angle's 2t. So you have 2t is pi over 2 and 3 pi over 2, but you add on those circular adjustments like that. And so now we got to isolate t, we got to divide these all by 2. And so you end up with pi over 4 plus k pi and 3 pi over 4 plus k pi. So now we're looking for solutions in 0 to pi. This one's nice. At k equals 0, we get pi over 4 and 3 pi over 4. At k equal 1, you're adding pi, but we're staying in 0 to 2 pi, so we already know k equals 1 is going to be too big. So we just get those 2 points. And remember, we're just expecting 2 horizontal tangents. Now, to get the xy coordinates, we need to plug in t equals pi over 4. That was also a y-intercept. We just did that. It's 0, 3. All right. And then you go and plug in 3 pi over 4. You get 2 cosine 6 times this. Now you end up with cosine 9 pi over 12. 9 pi over 12 is beyond one rotation. So you got to think about the angle that would give you the same thing within one rotation, which is 3 pi over 2. Cosine 3 pi over 2 also equals 0. All right, and that's for the x. And then for the y, we plug in the same angle for, or the same time for y. You end up with the sine of 3 pi over 2, which is -1. So y is -3. So my point's 0, -3. Remember that we were expecting two horizontal tangents, and there they are right there. All right, now for vertical tangents, we're setting dx dt equals 0. Here's our equation for x. So we're differentiating the cosine. Remember that differentiates to negative sign. And then we got to use the chain rule, setting that equal to 0. Divide out your -12, you end up with sine 6t equal to 0. When does the sine equal 0? At 0 and pi. Add your circular adjustment, but that's equal to 6t. And now you got to isolate the t by dividing by 6. All right, 0 divided by 6 is 6. You divide this part by 6, the 2 and the 6 reduce to 1/3. Here, you divide this by 6, you get pi over 6. You divide this by 6, you get k pi over 3. Since these common denominators aren't the same and I'm getting ready to have to compute with them, I went ahead and computed to a common denominator. All right, so in 0 to 2 pi, I did this one a little bit different than I did the last one. So I just start with this first set of solutions. K equals 0 gives me 0. K equals 1 gives me pi over 3. K equals 2 gives me 2 pi over 3. All right, then I come over, and then if I go to k equals 3, I would end up with pi. I should have written that. It actually repeats itself. All right, then k equals 4, I'm going to jump out of my interval. All right, and then I come over to here. K equals 0 is pi over 6. K equals 1 is 1 pi plus 2 pi over 6. That's 3 pi over 6, but reduces to pi over 2. And then k equals 2 is 1 pi over 6 plus 4 pi over 6. That gives me 5 pi over 6. So there's the times where I have my horizontal tangents. Remember, we were expecting several. And so now we just go and crank through all those times. So t equals 0 gives me these two. Cosine of 0 is 1. Sine of 0 is 0. So that gives me the point 2, 0. All right, t equals pi over 3 is a little bit different, though. It's hard to see what that y-coordinate is from the graph. And so you go and plug that in. You end up with 2, for my x-coordinate, 2 cosine of 2 pi. Cosine of 2 pi is 1, so I just get 2. Now I plug pi over 3 into my y equation, though, and I'm trying to find the sine of 2 pi over 3. Sine of 2 pi over 3 is square root of 3 over 2. You multiply those, you end up with 3 square root of 3 over 2. All right, this video is already run long, so I'm going to shortcut it here. But you go through with all of those times, crank through all of those times there, and you'll see that you end up with those combinations of positives and negatives with the numbers that we've already seen. So our vertical tangents are these 6 points, which we expected. We just couldn't really see what the y-coordinate is on a lot of those. All right, hope that helps.